Welcome to a new chapter this week, which is about virtual memory. So what is virtual memory? We can think about it as a vast library that helps a computer manage its limited physical memory space more effectively. And so imagine we thought about the physical memory as a small disk or a workspace where you can only keep a limited number of books at a time, but you also have access to a massive library with an infinite collection of books. And so in this analogy, the small disk or workspace represents the main memory, which is limited in size, and it can only hold a certain amount of data or instructions at any given time. Just like you may sometimes have trouble fitting a limited number of books on your disk. And so same thing, the computer sometimes would struggle if you could only work with its limited physical memory. And so the library in this analogy is the virtual memory. It acts as an extension to the physical memory and holds additional data and instructions that are not fitted and cannot be fitted in the limited physical memory. And so when the computer needs to access data or instructions that are not in the main memory, it can actually swap out some of the existing data from main memory and bring in the required data from the virtual memory. Remember we talked about swapping last week? So this swapping process is similar to us returning a book that we borrowed from the library and borrowing a different book in place. And so you cannot have all the books on your disk at once, right? But you can always exchange them with the books in the library to have access to a broader range of information. So you cannot fit all the data and instructions at once in main memory, but you can always swap in and out. And so the entire program source code does not need to be in memory at the same time. So we only need part of the program in memory for execution. So therefore, imagine this strong ability to execute just partially loaded programs instead of entire program, okay? So this will give us less memory to run more programs at the same time, right? So if we only load partial modules, just necessary modules from the entire program, then we're going to have the ability to load multiple programs, and this will increase the CPU utilization and throughput in our system, right? And so the virtual memory provides multiple benefits. Mainly it allows the computer to run larger programs than the physical memory can actually accommodate, using storage space on the disk as a temporary storage to do swapping. So it also therefore enables us to do multitasking by efficiently managing the allocation of memory resources among the different processes that we can automate at the same time. And so you can think of virtual memory as the separation of the user's logical memory from the physical actual main memory. So virtual memory, it's like an imaginary memory area. And the purpose of virtual memory is to enlarge and expand the address space and the set of addresses that a program can access. And so, for example, virtual memory may actually contain twice as many addresses as the actual physical memory, right? And so a program that uses all of the virtual memory, then it won't be able to fit in main memory all at once, but just partial modules of it at a time. And so the computer can still execute partially loaded programs, right? And then the way we do that is just we copy into main memory those portions that are necessary at a given time for program execution. And then later on, when we need extra modules, then we load them again. So we swap things that we do not need currently out, and then we bring new portions of code back into to the memory. And therefore, the logical address space can be much larger than the actual physical address space. And so the logical address space, or the virtual address space, usually starts at address 0, and it's contiguous addresses until the end of the entire space. And then the physical memory is, as we saw before, is organized into frames, and then the memory management unit takes care of mapping the logical addresses into the physical addresses. And so one way to implement virtual memory is using a technique called demand paging. So we talked before about paging. Now let's discover what demand paging is. So in simple words, demand paging means to only bring a page into memory when we actually need it, okay, not before. And this will provide us many benefits, namely increasing the CPU utilization. We're going to have less memory needed, and so we're going to have space to admit more processes, and therefore we can have more users and increase the throughput, and decrease the response time, and so on. And so the idea with demand paging is, once we need a page and then we go look for it in memory and we find that it's not there, so we call it not memory resident, means that page is not yet in memory. And so once we detect that it's non-resident, then we go ahead and load the page from the secondary storage. So once there is a demand, then we do page it. Therefore, that's where the name comes from, demand paging. So if the page was already there, it's already memory resident, then we're talking about the same thing as paging that we did before. So same principle applies, okay? And so one way to detect or identify if a page actually is in memory or is memory resident, we can use, again, hardware support. We can use a bit. So in the textbook, they call it the valid invalid bit. In Zybooks, they call it the present bit. But the main idea is it's a bit that once it's set to 1, this means that that page is actually in memory. It's already loaded to the physical memory. If it's set to 0 or invalid, this means that that page is not memory resident. It's not yet loaded into memory. So once the address mapping happens, and then we go look for a page in the page table, but then we find the valid invalid bit, or the present bit, is set to 0, meaning the page is not yet loaded to main memory. What happens is something that we call a page fault. So page fault defines as the act of not finding a page that we're looking for already loaded in main memory. And so page fault is a problem, right? Because we're looking for a page, but we didn't find it. And so how to handle page faults? And so the process goes as follows. So we have our logical space, right? And the CPU is looking or is referencing for a page. And so automatically we go to the page table, assuming that we've already checked the TLB and it's not there. And so once we check the page table and we found the index for that page, however, its present bit, or the valid invalid bit, is set to 0, so it's invalid. Then what happens is we generate a trap to the operating system saying that a page that the process needs is not yet in memory. So the operating system will go ahead and try to find that page in the backend store or in the secondary storage. Once it's found, then we go ahead and bring it to and load it into an empty frame in the physical memory, and then we go ahead and reset the process where it last ended. And so one extreme case of demand paging is when we start a process with no pages in memory at all. So when the process will attempt to start executing, it will look for the first page and it won't find it in memory, and a page fault happen. So this is called pure demand paging. So usually we do not do pure demand paging, but instead we start a process with a minimum number of pages that are preloaded into memory. Then the rest will be loaded on demand. And so to handle page faults and demand paging in general, we do need hardware support. And so we need the valid invalid bit in the page table to represent if a page is memory resident, and then we need secondary storage, right, to swap in and out from the backend store, and then we need ways to restart the instruction after handling the page fault. And so all these operations do take some time, right? And it's part of the latency. And so, for instance, to service an interrupt, it may take between 1 to 100 microseconds to read a page, especially from a typical hard drive disk. Then maybe we need 8 milliseconds to restart the process. At the last instruction, we may need 1 to 100 microseconds. And then if we define the page fault rate as P, which is again just like the hit ratio that we talked about before with TLBs, so it's between 0 and 1, and it represents the rate of how often we're having page faults in our systems. And so if P is 0, this means that we don't have any page faults at all. And then if it's 1, then every reference that has been made is actually a page fault, right? So the P, which is page fault rate, will fall somewhere in between, right? And so if we imagine that, if we assume that the memory access time actually takes 200 nanoseconds, then the effective access time in this scenario will be equal to the page fault rate times 8 milliseconds, because in this case a page fault already happens, right? And then we do have to go to the backend store and read the page from it. And this, as we said, it may take somewhere around 8 milliseconds. And then if there is no page fault, which is 1 minus P, then we just need 200 nanoseconds to access the physical memory where the page is already resident, right? So that's the effective access time. So here we ignored all the other aspects that have to do with servicing the interrupt and restarting the last instruction, when we only considered the time it takes to load the page from the hard disk. And so we defined V as the valid invalid bit, right? Which represents if the page is actually resident in the memory currently. And so when V is equal to I, right, which is invalid, then the corresponding page is where? Is it only in the physical memory or only on disk or both? So since it's invalid, this means that it's not actually in physical memory and it's only on disk. We haven't loaded it yet to physical memory. Now, once the bit equals to V means valid, automatically this means that it has already been loaded to the physical memory from disk. So it is resident on both the disk and physical memory. And so if a process executes this code, right, branch M, and then M is actually loading the value of X to the register of R. So the question says, if we execute this code, then how many page faults we may end up with. And this assuming that the branch instruction is already memory resident. So branch is already there. We do not need to load it. And M is this instruction, okay? So branch is already there. We don't have to worry about it. Then we are left with load and X, right? So now there is multiple possible scenarios. If none of these two is memory resident, then we're going to end up with 2 page faults. If just one of them is memory resident, then we may end up with just 1 page fault, right? So if X is, or if load instruction is already there, but we don't have the variable X yet loaded, then we only gonna have 1 page fault for X. If X is already there, but the load instruction hasn't been loaded yet, then we're gonna end up again with just 1 page fault for the load instruction. Now, if both of them are already loaded in memory, then we may end up with 0 page faults, right? Since branch is already there, and X is already there, and load instruction is already there. Okay, so there's 3 different possibilities, either 0 or 1 or 2. And so part of the demand paging and handling page faults, we said that once a page is not memory resident, then we go ahead and go to the backend store or the disk and load that page into a free frame in the physical memory, right? So what happens if the entire physical memory is full and there is no free frame to load our page into? Then we need some alternatives, right? So one way we thought about it is to do swapping, right? That's one solution. Do we terminate processes to empty physical memory? Not really. That's not a practical solution, right? Because remember, processes may be in the middle of doing something important, and just terminate them in the middle of execution is not really a practical solution, and may have to restart them all over again. And if it's a process that needs a lot of heavy processing, it takes time, then it was almost done and you stopped it there, and then it has to go restart the entire process again. So no, we don't terminate. We may swap, but there is also an alternative, which we're going to talk about next, which is replacement. So we need an algorithm that can tell us which out of these frames we can actually replace with the newly loaded one. And so the idea is, once we are looking for a page in the page table and we see that it's invalid, we go ahead to look for it in the backend store, and we want to load it, but our physical memory is full. So now we're faced with this question. I want to execute page replacement, but which one to replace out of these, right? And there are multiple algorithms that we will learn that enables us to do page replacement in different ways, but to compare them, and the final goal is to pick the algorithm that will result in actually the minimum number of page faults. We want the page fault rate to be as small as possible.